everyone, and welcome to this Applied Remote Sensing training on NASA Earth observations for reservoir and water utility management. My name is Amita Mehta, and this training series will be conducted by my colleague Sean McCartney and myself from NASA Goddard Space Flight Center. We will start with a brief introduction to the Applied Remote Sensing Training or ARSET program. ARSET provides cost-free training on the use of satellite and Earth system model data for applications across various thematic areas including agriculture, disasters, ecological conservation, health and air quality, water resources, and wildland fires. ARSET trainings are tailored to audiences with a variety of experience levels from introductory to advanced. The ARSET trainings are offered either online or in person. They can be live and instructor-led like this one or taken asynchronously as self-paced training available from NASA ARSET website. ARSET utilizes open source software and data, and several trainings are conducted in Spanish in addition to English, and all training materials are translated into Spanish. Before we start, there are a number of recommended prerequisites. These are past ARSET trainings available from the links provided here. Fundamentals of remote sensing. It provides basic information on principles of remote sensing about various satellites and sensors and how they measure geophysical parameters. Introduction to NASA's snow and ice data products and applications for water resources management describes snow-covered data from satellites. It's highly relevant for reservoir management with inflow from snow-fed rivers. Monitoring global terrestrial surface water using remote sensing. This training provides data, information, and tools for monitoring water levels of reservoirs and rivers. And finally, monitoring and predicting floods using Earth observations. It introduces GeoGLOS, a hydrologic forecasting model that provides information about water inflow and outflow in and out of reservoirs. Here's the outline of this training. There are three parts to this training. Part 1 today will focus on data requirements for reservoir management. Part 2 will focus on accessing these Earth observations for reservoir management. And finally, Part 3 will talk about applying NASA Earth observations specifically to hydropower reservoir management. There will be one homework assignment posted on the ARSET website on 11th of August, which is the last day of the training, and the homework will be due on 25th of August. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the due date. Before we dive into today's session, there are a few important facts and concepts to note. As we know, water is critical for drinking, agriculture, industries, hydroelectric power generation, public health, and transportation, among other usages. Now, despite the vast amount of water on Earth, so 71% of Earth is covered with water, but out of that, 97% is in our oceans and it's saline. Only 2.5% is fresh water, which is usable for these applications, and out of that, only 1.2% is surface water, including lakes and rivers, which contain 21% of total surface fresh water. So ultimately, it is really a very small amount of water that needs to be carefully managed for all these applications, and that's why reservoir management is quite important. Satellite remote sensing helps monitor surface water extent, water levels in reservoirs and rivers, and their surrounding watersheds. Satellites measure optical, infrared, and microwave radiation, either emitted, reflected, or backscattered by the Earth system, and that allows us to detect water measurements. The overall learning objectives for this training are that by the end of this series, you will be able to recognize the importance and availability of Earth observations and model data for reservoir management, identify NASA Earth observation products applicable to reservoir management, focusing on key hydrological parameters such as precipitation, soil moisture, snow cover, snow water equivalent, runoff, water surface elevation in reservoirs and tributaries, and simulated stream flow in inflow rivers from a global hydrologic model. Access and visualize the Earth observation parameters using relevant web tools such as WorldView, Global Water Measurements, SWOTWiz, and Google Earth Engine to monitor critical watershed conditions upstream of reservoir inflow and also water levels in reservoirs. Use the GeoGLO's River Forecast System RFS hydrology model to query historical river data and construct predictive stream flow hydrographs for inflow rivers. Finally, analyze time series of Earth observation parameters for a given river basin boundaries and hydropower reservoirs of interest. How to ask questions. To ensure we see your question, please locate the 3 dots at the bottom of your training window. You will see a Slido Q&A option. You may also see a standalone Slido tab or app. We will address all questions relevant to the training topic at the end of the webinar. Feel free to enter your questions as we go, and we will try to get to all the questions during the question and answer session after the webinar. The remainder of the questions will be answered in the question and answer document, which will be posted on the training website about a week after the training. Both Sean McCartney and I are instructors with ARSET, and as I mentioned earlier, we will be co-conducting this training series. We will take turns in presenting the material, covering various sections of today's presentation and demonstrating some of the tools we mentioned. I am a research associate professor and applied research scientist at NASA's Goddard Space Flight Center and the University of Maryland, Baltimore County, Goddard Earth Sciences, Technology and Research Center. My primary interest and experience are in satellite remote sensing of geophysical parameters and their analysis and applications for understanding weather, climate, and hydrologic processes and developing trainings for water resources and disasters management. Sean McCartney is an earth scientist at NASA's Goddard Space Flight Center. Sean, for ARSET, focuses on developing trainings with applications of NASA satellite and model data for decision making. He develops specialized training related to agriculture, disasters, and water resources management. He focuses on combining earth science and remote sensing expertise through comprehensive training programs to enhance the technical capabilities of individuals and institutions in applying NASA earth science data. Objectives for today is that by the end of part 1, you will be able to identify the key challenges, operational factors, and data requirements associated with reservoir management, determine the relevant NASA Earth observation datasets that can support management efforts. We'll start with this training series on Earth observations for reservoir and water utility management. Now, a reservoir is a man-made lake and where water is stored, and most reservoirs are created by damming a river which traps the natural flow to form a storage basin. An example of San Carlos Reservoir is shown here, where water is stored in this reservoir. A World Bank review in 2023 of global and regional datasets estimated the number of large dams and reservoirs at 35,000 to 62,000, and the US National Inventory of Dams reported 90,000 plus dams in the US. Historically, one of the world's oldest known dams, the Java Dam in modern-day Jordan, was built around 3000 BC, and that was for irrigation. Most of the world's existing dams were constructed after World War II, driven by the push for global economic development. Modern reservoirs are multi-purpose infrastructure systems, and they are used for water supplies, agricultural irrigation, mitigating flood risks, hydroelectric power generation, and public recreational spaces. This animation is of Landsat images, true color images between 1985 and 2025, and it shows the Amistad Reservoir on the US-Mexico border. And it's interesting to see that over the years, it shows how water extent in this reservoir is changing as well as water quality. As you can see, the colors potentially indicate algal bloom in the reservoir. There are two types of reservoirs, on-stream and off-stream reservoirs. On-stream reservoirs, they are built directly on a river using a dam to capture natural flow. They are used for large-scale hydropower, flood mitigation, and downstream flow regulation due to their massive storage capacity. And off-stream reservoirs, they are built away from the main river channel and filled with diverting or pumping water into a storage basin. They are commonly used for municipal drinking water supplies, specialized agricultural irrigation, and pumped storage hydropower. Here is a figure that shows an example of an off-stream reservoir. This is Landsat 7 image showing the San Luis Reservoir in California. This reservoir stores water taken from the San Joaquin and Sacramento River Delta. Now, reservoir management is really important because reservoirs are used for water supply, securing drinking water for municipalities, and sustaining agricultural irrigation. Used for flood mitigation, protecting downstream communities by capturing and regulating extreme runoff. For hydropower generation, providing reliable, renewable hydroelectric power to the grid, including run-of-the-river, base load storage, and peak load, which we will be discussing further in session 3. Finally, for recreation, they are used supporting local economies through public access for boating, fishing, and water sports. There are also management challenges for reservoirs. First of all, there are competing timescales. On short-term timescale, so hours to days, management requires rapid decision-making for peak hydropower generation, daily market demands, and immediate flood mitigation. On long-term, so seasonal to interannual timescale, management requires strategic planning based on predicted runoff volumes, snowpack assessments, and seasonal water supply forecasts. Also, data blind spots, they are a challenge. Monitoring ungauged mountain basins and low elevation snowpack is difficult because there are no ground-based measurements available. Yet, this information is vital for assessing how much water will flow into a reservoir. Water quality, while dropping water elevations and rising temperatures, they can trigger harmful algal bloom. They're hard to monitor. And finally, transboundary coordination. When a river or reservoir crosses state or international borders, synchronizing operations across those boundaries is very challenging. To meet some of these challenges, remote sensing data can be highly useful. So in the remainder of sessions, we will discuss the NASA Earth observations and Earth system models that are useful for monitoring reservoir and watershed conditions. For reservoir management, we require both watershed hydrology and meteorology parameters, as well as parameters relevant to the reservoirs themselves. Watershed hydrology and meteorology parameters include land cover, precipitation, runoff, snow cover, snow melt or snow water equivalent, soil moisture, topography and stream network, and weather data such as wind speed, temperature, humidity, solar radiation, and vegetation, which are useful. They control transpiration in the watershed and evaporation from the reservoirs. Reservoir parameters include bathymetry, reservoir water level, sedimentation, seepage and evaporation, water inflow and outflow. So stream flow from upstream rivers, and for outflow, schedule release for downstream supply usage and power generation. So all this information is needed for effective reservoir management. NASA Earth observations, they provide reservoir management data sets. So first of all, here is a list of watershed parameters. It includes land cover from Terra and Aqua satellites or MODIS sensor, SNPP, NOAA 20 and 21 VIIRS, Landsat 8 and 9 OLI, and Sentinel-2 MSI. These are optical measurements. They're used for land cover derivation. Precipitation is available from Global Precipitation Measurement and an international constellation of satellites with microwave radar, radiometers, and imagers. Runoff and snow water equivalent, they are available from Global Land Data Assimilation System and North American Land Data Assimilation Systems. These are land surface models, and so these data are available based on modeling. Snow cover also is available from Terra, Aqua, SNPP, NOAA 2021, similar to land cover. Soil moisture is available from Soil Moisture Active Passive. Topography and stream network, they are available from a tool, Hydrosheds, and weather data, they're available from GEOS 5 and MERA 2 models in near real time, and also weather forecasts available for several days. In this presentation, we will focus mainly on land cover, precipitation, runoff, snow cover, snow water equivalent, soil moisture, and we will also look at hydrosheds for different river basins. We will briefly talk about this model, but this is going to be part of our future training where we talk about short-term forecast for meteorology and hydrology parameters. NASA observations for reservoir parameters are available. Bathymetry is available from ARSET 2 satellites. It's a LiDAR that provides bathymetry. Reservoir water level heights available from SWOT satellite, Sentinel-6, JSON-2 and 3 satellites based on radar altimeters. Sedimentation is available from Landsat 8 and 9 and Sentinel-2 satellites. Now seepage, this has to be derived using models and water height observations. And water inflow and outflow, they are available from GeoGLO's hydrologic model that provides stream flow. And for outflow, we also need to know in situ data for water usage, such as water release for different applications. For this presentation in this series, we will focus on reservoir water level height and inflow and outflow to monitor reservoir parameters. Next, we will learn about details of some of these data sets, and we will have demonstration of some web tools through which these data can be visualized. So I'm going to hand it over to Sean McCartney. He is going to talk about precipitation, soil moisture, snow cover, and some other parameters. So Sean.
Thank you, Amita. Today, I will be discussing the critical role of iMerge precipitation data in watershed and reservoir monitoring. Water managers rely heavily on ground networks like stream gauges and reservoir sensors. However, these networks often have spatial gaps, especially in complex terrain or areas where we are currently flying blind without sensors. That is where satellite-based products like iMerge come in. iMerge provides spatially distributed, gridded precipitation data that offers immense value upstream of our physical gauges. Moving on to how we actually capture the iMerge data, we rely heavily on two dedicated precipitation measurement missions, TRIM and GPM. TRIM stands for the Tropical Rainfall Measuring Mission, and GPM is the Global Precipitation Measurement Mission. Both are highly successful collaborative efforts between NASA and the Japanese Space Agency, or JAXA. These satellites are specifically designed to measure precipitation from space, utilizing a combination of active and passive microwave observations to give us accurate rainfall rates. TRIM was a pioneer in the space, operating from 1997 until 2015. To ensure we did not lose this vital monitoring capability, GPM was launched in 2014 and continues to operate today. For watershed monitoring and hydrologic modeling, the real value here is the continuity. Combined, TRIM and GPM provide an uninterrupted record of nearly 30 years of precipitation data. This deep historical archive is exactly what allows us to establish accurate climatological baselines, calculate those critical seasonal anomalies, and confidently support long-term water management decisions. Now let us look at how these missions generate the data. The TRIM and GPM core satellites do not operate alone. They actually serve as a reference standard to calibrate microwave observations from a broad constellation of national and international satellites. As you can see in the visualization on the right, leveraging multiple satellites gives us significantly improved spatial and temporal coverage. This means more frequent data updates and fewer blind spots over our watersheds. To process this constellation data, we use specific multi-satellite algorithms. TRIM relied on the TMPA algorithm, while GPM uses the current iMerge algorithm. For water managers and hydrologic modelers, the critical piece here is continuity. The modern iMerge data is carefully calibrated against the historical TMPA baseline. This backward calibration creates a seamless, long-term precipitation record. This continuous data set is exactly what we need to feed into hydrologic models, understand long-term basin dynamics, and support those critical 12 to 18-month runoff forecasts for reservoir management. Let's look at the actual data product we use, iMerge. It is a highly capable, integrated system that provides both near real-time and historical precipitation data. Because different decisions require different timelines, iMerge offers 3 runs. The early run is available in just 4 hours, making it vital for immediate flash flood monitoring. The late run is available in 14 hours, and the final run takes 3 months, providing the highest accuracy for long-term reservoir planning and hydrologic modeling. The product operates on a 0.1 degree global grid with true pole-to-pole coverage, and its continuous temporal record stretches all the way back to 1998, which is essential for our baseline models. If you look at the visualization on the right, you can see iMerge in action over a week-long period from June 30th to July 7th. The greens and reds in the lower latitudes indicate liquid precipitation, while the blues and purples in the higher latitudes represent frozen precipitation such as snow and ice. This ability to differentiate between rain and snow events is absolutely critical when we are trying to estimate snow water equivalent and predict seasonal runoff volumes into our reservoirs. Bringing this all together, how do we actually apply iMerge data to reservoir and watershed management? First and foremost, iMerge allows us to measure precipitation across an entire watershed, capturing data in remote areas where physical ground gauges simply do not exist. This is especially vital for filling observation gaps in topographically complex or ungauged sub-basins, where water managers might otherwise be flying blind regarding upstream rainfall. For short-term operations, iMerge tracks extreme weather events such as atmospheric rivers in near real time. This gives operators the situational awareness needed to make critical, rapid water release decisions for flood control. Additionally, tracking this rainfall helps us assess precursor conditions, like overall basin saturation, allowing us to better predict how much of a storm will actually translate into runoff versus being absorbed into the soil. Finally, by monitoring long-term precipitation anomalies, we can better anticipate extended dry periods, manage droughts, and support our long-term water supply planning over that crucial 12 to 18-month horizon. For those interested in diving deeper into how the data is processed, I've included a link to the full technical documentation at the bottom of the slide. I will now transition to a short demonstration using the web-based NASA Worldview application. I will walk you through how to search for, access, and visualize the iMerge precipitation data. If you want to follow along, click on the hyperlink provided on the slide. For those that are following along, click on the link provided at the bottom of the slide. This will take us to the NASA Worldview landing page. The first thing we see is a window with curated stories provided by the NASA Earth Data team. I encourage you to click and explore these different stories on your own time, but for the sake of this demonstration, I'm going to close out this window. I'm going to turn our attention to the left-hand side of the application. Underneath the NASA Worldview banner, we can see that we have 3 different tabs. The furthest on the left is a Layers tab. These are default reference and base map layers that are provided by the application. The middle tab is an Events tab. This is showing all the current events such as floods, fires, and other events happening on the planet. And then to the right, we have a Data tab, and this is where you can download any of the data found within this Layers tab. To turn on or off any of these layers found under reference or base map layers, to the left of any of these layers, there's an eye icon to either hide or to show that layer. Personally, I like the coastlines, borders, and roads reference layer, so I'm going to turn that on. And for the base map layer, I'm going to go ahead and turn on the Blue Marble Modus layer, cloud-free from 2004. Now, to add the iMerge precipitation data that we're interested in, if we look at the very bottom of the Layers panel, there's a red button that says Add Layers. I'm going to go ahead and click on that, and a new window pops up with different tabs for hazards and disasters, science disciplines, as well as featured layers. I encourage you to explore all of these on your own. It's a wealth of data that NASA provides, but because we know we're specifically looking for iMerge data, I'm going to go ahead to the search bar and type in iMerge. 2 different options are presented. We have a 30-minute data set as well as a daily data set. And to add any of these to our layers panel, we can do that in 2 ways. I'm going to click on either of these layers. In this case, it's the daily layer. I can either click on the box next to that and it adds that layer, or on the right, where it provides more information about that data set, there's also an option to add the layer here. I'm also going to go ahead and add a Reservoirs layer, which the Worldview team also provides. So I'm going to go ahead and click on that, and I'm going to close out this window. So now we have a reference layer, a base map, as well as a iMerge precipitation daily rate, as well as a reservoir layer. So we've got everything we need to start exploring this different data. And to query based on the date, month, day, month, and year, we can do that using the buttons down here, or we can use the slider to specify the date that we're interested in. In this case, I'm going to go back to July 15th, and at the top of the window, I'm going to click in the search bar, and I'm going to search for a specific reservoir called Lago Calbun. Lago Calbun is found in South America, specifically in Chile, the country of Chile. You could be searching for any other reservoir that you might be interested in, so feel free to explore this based on your area of interest. For the sake of this demonstration, I chose this reservoir in the country of Chile. I'm going to go ahead and zoom in a little bit closer. This is one of the largest reservoirs in the country. And we can see that from the course of July 15th, July 16th, 17th, 18th, and 19th to the 20th, we had both liquid precipitation to the west, and then to the east in the higher Andes, we had solid precipitation such as snow and ice falling over the Andes. And if we wanted to generate any statistics based on this, if we look at the bottom of the layers panel, there is an option to start charting. If I click on that button, we can see that a bounding box appears. I can move this bounding box around. I can enlarge it. I can do many things with it. In this case, I'm just going to position it roughly over Lago Calbun or Lake Calbun. And then if I look back down underneath the layers panel, there's a generate chart in red. I'm going to go ahead and click on that. This is going to provide us with a 10-day statistics of precipitation rate. This is millimeters per hour, and we can see going from July 10th to July 20th, it's showing the mean precipitation within that bounding box. But it's also providing other statistics such as median, the min-max, and standard deviation. So a really quick way to start exploring iMerge precipitation data for your area of interest. This has been a very quick demonstration on how to access and visualize and explore iMerge precipitation using the Worldview application. But now we're going to go on and start talking about SMAP soil moisture data. Now that we have covered how to track the water falling into our basins, we will shift our focus to what happens once that water hits the ground. Over the next few slides, I will introduce the Soil Moisture Active Passive, or SMAP, mission and its specific data products. We will explore why monitoring soil moisture is another critical component for watershed management, particularly for understanding basin saturation, seasonal runoff potential, and flood hazards. Think of the soil as a giant sponge. Knowing exactly how wet or frozen it is across the watershed is critical for predicting how much rain or snowmelt flows directly into a reservoir versus soaking into the ground. To monitor this, we use the SMAP mission launched in January 2015. This satellite remains essential for our hydrologic modeling. Its primary objective is measuring moisture in the top 5 centimeters of soil globally, providing updated observations every 2 to 3 days. SMAP achieves this using microwave technology. This allows continuous monitoring because microwaves easily penetrate cloud cover and vegetation canopies, operating both day and night. The sensor is highly sensitive to water content because moisture fundamentally changes the Earth's microwave dielectric properties. The image on the right gives a great visual representation of this concept. It clearly illustrates how wet, saturated soils in a field are noticeably less reflective to these signals than the drier surrounding soils. The system uses a 1.41 gigahertz radiometer with a 40 kilometer spatial resolution. This frequency is highly sensitive to soil moisture while minimizing interference from vegetation or weather. The spacecraft features a massive 6-meter rotating antenna that maintains a 40-degree incidence angle, sweeping a 1,000 kilometer swath across the Earth. SMAP flies in a sun-synchronous orbit at an altitude of 685 kilometers, capturing data during passes at 6 a.m. and 6 p.m. local time. The combination of the specific orbit and wide swath enables complete global coverage every 2 to 3 days. This rapid revisit time provides continuous updates on changing soil conditions, allowing us to quickly adjust runoff models and flood forecasts as storms approach. To actually use SMAP data, we access it through the National Snow and Ice Data Center, where it is organized into 4 distinct processing levels depending on your modeling needs. Level 1 contains the raw instrument measurements. However, for watershed management, we typically start with Level 2, which translates those raw signals into actual soil moisture retrievals. Level 3 is highly useful for runoff forecasting as it provides daily composite maps that include both soil moisture and freeze-thaw states. Knowing if the ground is frozen is critical for predicting whether a sudden rain event will trigger immediate flooding or soak into the soil. Level 4 takes this a step further by providing model-derived root zone soil moisture, which is incredibly valuable for assessing deeper seasonal basin saturation and drought conditions. These products are available at 3, 9, and 36 kilometer spatial resolutions. With a continuous global record dating back to 2015 and updates every 1 to 2 days, SMAP gives us a highly reliable, near real-time dataset to predict exactly how our watersheds will respond to incoming storms. So how do we actually apply these SMAP products to our daily reservoir and watershed operations? First, it gives us a clear picture of antecedent soil moisture. By knowing how saturated a basin is before a storm hits, we can accurately predict if incoming rain will safely soak into the ground or immediately trigger rapid flood runoff. This feeds directly into enhanced runoff modeling. By incorporating SMAP's surface and or root zone soil moisture data, our hydrologic models become significantly more accurate at forecasting actual reservoir inflows. SMAP also tracks freeze-thaw states. Detecting exactly when frozen ground begins to thaw is a crucial signal for anticipating the onset of seasonal snowmelt and spring runoff. On the flip side, during dry periods, assessing deep soil dryness is essential for drought monitoring. This long-term data guides critical water conservation efforts and hydropower release schedules over the season. Finally, it supports hazard mitigation by identifying highly saturated, unstable slopes. Recognizing these landslide risks Early helps protect critical dam infrastructure and maintains downstream water quality. I will now transition to another short demonstration using the web-based NASA Worldview application. This time, I will walk you through how to search for, access, and visualize SMAP soil moisture. If you're following along, click on the link provided at the bottom of the slide, which will launch the Worldview application. I'll close out the default pop-up window and then go to the left-hand side of the application where we find the Layers tab. And for reference layers, I'm going to hide the coastlines and I'm going to turn on the 2 layers above it, which are place labels as well as coastlines, borders, and roads. And as a base map layer, if we look in the map window, we can see that there are some black data gaps with the MODIS instrument. It does not provide complete coverage due to the swath width of the MODIS instrument. So to get full global coverage, I'm going to select the NOAA 21 VIIRS instrument, which if I change the date, we can see that there's no orbital gaps in data coverage for this instrument. So now that we have our base layers and reference layers selected, I'm going to go similar to what we did with the iMerge precipitation. I'm going to go to this red Add Layers button at the bottom of the Layers panel. And once I select that, I'm going to go to the search bar and type in SMAP, and then L4, which is the level 4 product, and then I'm going to type in moisture. So we have 4 different options for the level 4 soil moisture products. We have root zone soil moisture, which is 100 centimeter depth soil moisture product. We also have the uncertainty of that product. We have the surface soil moisture, which is to the 5 centimeter depth, as well as the uncertainty there. I'm going to go ahead and add the surface soil moisture, which is the 5 centimeter depth, because I want to compare this with the level 3 product, which only provides that skin, that top skin, that 5 centimeter soil moisture as well. So with selecting the level 3 soil moisture product from SMAP, we can see we have a number of different options. We have soil moisture 9 kilometer at day and night. The day is the 6 a.m. overpass. The night is the 6 p.m. overpass. We have a couple options for 36 kilometer, all using this passive L-band radiometer. And then we have 2 active options where if I click into either of these, if you look on the information panel on the right, we can see that the data is only good for the year 2015 for both of the 3 kilometer and 9 kilometer. The reason being, in early July, the active radar on the SMAP mission failed, and so it's no longer functioning after July of 2015. So for this demo, I'm going to click on the passive daytime 9 kilometer level 3 product so that we can compare both level 3 and level 4. And then lastly, I'm going to add the reservoirs layer similar to what I did before so that we have a base layer of global reservoirs. And now that we have all the layers that we want for this demonstration in the Worldview application, I'm going to choose to go to the monsoon season in the state of Arizona for this demonstration, but of course, you could pick anywhere you are interested in terms of geography on the planet. The monsoon season in Arizona is typically in the month of August, so I'm going to go ahead and change the date, the start date, to 2025 and August 1st. And what I'm going to do in the search bar at the top of the map window, and you could type in anywhere you would like to look at, but I'm going to type in Theodore Roosevelt Lake. And Theodore Roosevelt Lake, when I click on that, it will zoom to that reservoir or that lake, which is in the state of Phoenix, and it's roughly 80 miles outside of the city of Phoenix. It provides both drinking water, flood control, as well as hydropower for the largest city in the state of Arizona. And now that we have the study area picked and the layers that we want, I want to show you the difference between the level 3 and level 4 SMAP product. So if I hide the level 4 product and we just have the level 3 product showing, and again, we're zoomed into the state of Arizona, if I advance by day in August, the month of August of last year, 2025, we can see that the coverage from the daily SMAP level 3 product is not daily. It's typically every 2 to 3 days, we're going to get overpasses over the study area, which is in this case, the Phoenix area and the Theodore Roosevelt Lake. But it's not going to be daily coverage for this month or for any month. But then if we go back to August 1st. And if I hide this layer and turn on the level 4 SMAP soil moisture product, which again is a modeled product, it's taking the same data, the same instrument, the sensor, that L-band radiometer from the SMAP mission, but it's assimilating it into a land surface model so that we have complete daily coverage. So there's no gaps in data. And now as I advance, we can see not only do we see the heterogeneity of soil moisture during the monsoon season, but we can also see that we have daily coverage, and it's not just for Arizona, but it's global daily coverage using this level 4 modeled product. So this is one quick way to start exploring SMAP soil moisture data, both level 3 and level 4. You can choose any study area that you want. In this case, I chose the reservoir outside of Phoenix in the state of Arizona, just so that we could see the heterogeneity of soil moisture during the monsoon season. But also I wanted to point out the differences between both the level 3 and level 4 modeled product or non-modeled product. Now that we have covered how to access and utilize soil moisture data for our basins, we're going to shift our focus to snow cover. Over the following slides, I'll introduce key NASA and NOAA missions designed for monitoring snow extent. We will explore why tracking snow cover is another critical component for effective watershed management, particularly when it comes to understanding seasonal runoff, spring forecasting, and long-term water supply. Let's look at how snow and ice act as massive natural storage reservoirs for our watersheds. When precipitation falls as snow at high latitudes or high elevations, that water is effectively locked away and stored in place for days to months. On a much longer timescale, glaciers, which are formed from snow accumulating over many years, can store immense volumes of water for hundreds to tens of thousands of years. For reservoir operations, this delayed release is absolutely critical. Meltwater from snow and ice provides a major contribution to overall basin runoff, especially in regions that typically see very little precipitation during the spring and summer months. To give you a visual sense of the scale, the image on the right is a MODIS True Color image from NASA Worldview. It shows the extensive snowpack across the Rocky Mountains near Denver, Colorado, just ahead of the spring melt season in late March 2013. Monitoring the full extent of the snow cover is essential. It directly drives the seasonal runoff forecasts that water managers rely on to balance water supply, manage flood control, and plan hydropower generation throughout the rest of the year. To effectively monitor snowpack for our reservoirs, we rely on 4 main types of remote sensing instruments, each providing a unique piece of the hydrologic puzzle. First, we use passive microwave sensors. Snow naturally scatters the microwave emissions coming from the Earth's surface. By detecting these changes in emission, sensors can help us estimate the overall snow mass across large basins. Second, we use visible wavelengths. Because snow is highly reflective, we can use its bright albedo to easily distinguish snow-covered areas from bare ground. This is absolutely vital for tracking the retreating snow line during the spring melt season. Third, for actual depth measurements, we utilize LiDAR. By measuring the distance to the bare ground in the summer and comparing it to the snow-covered surface in the winter, we can calculate highly accurate snow depths, which is critical for estimating total water volume. Finally, active radar, or SAR, provides extremely useful backscatter data. These radar signals are sensitive to the physical properties of the snow, helping us detect exactly when the snowpack is ripening, melting, and preparing to release runoff into the watershed. Diving deeper into how we observe snow, let's look at its unique spectral signature. In the visible wavelengths, snow has an incredibly high and consistent reflectance. Simply put, this is why snow appears bright white to both our eyes and our optical sensors. However, as we move into the shortwave infrared and thermal infrared wavelengths, snow behaves very differently. It actually absorbs most of the energy in these ranges, resulting in very low reflectance. You can clearly see this specific spectral curve in the graph at the bottom of the slide, which maps wavelength in micrometers on the x-axis against percent reflectance on the y-axis. Notice how the blue line, representing snow, spikes high in the visible spectrum on the left and drops off sharply as you move into the infrared on the right. By comparing this distinct curve against the other land cover types shown on the graph, such as rock, vegetation, and water, we can train our satellite algorithms to easily isolate and map snow-covered areas. For watershed management, this precise mapping is exactly what allows us to track the retreating snow line week by week and accurately forecast spring runoff volumes for our reservoirs. To actually capture the unique spectral signature of snow we just discussed, we rely on a specific set of advanced multispectral sensors. The foundational workhorse for this has been MODIS, or the Moderate Resolution Imaging Spectroradiometer. It flies on both NASA's Terra and Aqua satellites, which have been providing continuous daily snow-cover data since 1999 and 2002, respectively. To ensure we maintain these critical observations into the future, we now also use VIIRS, or the Visible Infrared Imaging Radiometer Suite. This instrument flies on a newer generation of satellites, including Suomi NPP, NOAA 20, and NOAA 21. For watershed managers and hydrologists, the overlap and transition between MODIS and VIIRS is incredibly important. Together, these sensors provide an unbroken, multi-decade record of global snow cover. Having this deep historical archive allows us to confidently compare today's snowpack extent against historical averages. This context is essential for building accurate seasonal runoff models, predicting water availability, and guiding long-term reservoir operations. This table shows the specific spectral channels MODIS and VIIRS use to capture snow data. The visible channels, red, green, and blue, detect the bright white reflectance of the snowpack. Crucially, these fall within atmospheric windows. These are wavelengths where the atmosphere is mostly transparent, allowing sensors to see the Earth's surface clearly. Shortwave and thermal infrared channels are essential for distinguishing snow from clouds and monitoring surface temperatures as the snowpack ripens. Although MODIS has 36 channels and VIIRS only 22, both possess the overlapping bands necessary to generate accurate, continuous snow products. Finally, while this table lists central wavelengths, the sensors actually capture a slightly broader range or bandwidth, ensuring the full signal is recorded. So how do we actually derive our daily snow cover maps from these MODIS and VIIRS sensors? It comes down to exploiting the specific spectral signature we just looked at. Our algorithms focus heavily on two key wavelengths. As shown here, snow has a very high reflectance in the visible red band, around 0.64 micrometers, but a very low reflectance in the shortwave infrared band, near 1.6 micrometers. We use that contrast between these two specific bands to calculate the Normalized Difference Snow Index, or NDSI. This index is the mathematical engine behind our automated snow mapping. This contrast is specifically what allows the satellites to tell the difference between snow and clouds. While both look bright white to our eyes in visible light, clouds remain highly reflective in the infrared, whereas snow absorbs that energy and appears dark to the sensor. By reliably filtering out the clouds, we can confidently map the true extent of the snowpack across complex mountainous terrain. These accurate cloud-cleared maps are then fed directly into our runoff models to forecast seasonal reservoir inflows. The Normalized Difference Snow Index, or NDSI, uses the difference between the visible and the shortwave infrared reflectance to map snow-covered areas. NDSI less than 0 is definitely not snow. This is typically bare ground or open water. An NDSI value above 0 is possibly snow. This often represents patchy melt or snow hidden under forest canopies. An NDSI above 0.4 is likely snow. This is our critical threshold for confidently mapping the continuous snowpack. And a caveat is that while snow always has an NDSI above 0, highly reflective water bodies or minerals can occasionally cause false positives. Applying these specific thresholds ensures our seasonal runoff forecasts are based on accurate snow extent. Here is a breakdown of the specific MODIS snow products we use to monitor our watersheds. As you can see in the table, these products generally offer a 500-meter spatial resolution. This level of detail is excellent for capturing snow extent across complex mountainous topography. We have multiple temporal options to fit different modeling needs. Daily maps are perfect for tracking rapid spring runoff. 8-day composites are highly effective at filtering out persistent cloud cover, And monthly means help us establish long-term water supply baselines. When searching for the data, pay attention to the product ID prefix. Files starting with MOD are from the Terra satellite, while files starting with MYD are from the Aqua satellite. Both provide an identical suite of products. All of these files are currently available in version 6.1 or collection 6.1. You can access them directly from the National Snow and Ice Data Center in HDF file format, ready to be imported right into your basin management workflows. Moving on to the newer generation of sensors, here's the suite of VIIRS snow products. A major advantage of VIIRS for watershed management is the improved spatial resolution. As you can see, the core products provide 375 meter resolution, which gives us even sharper detail over complex mountainous topography compared to the older MODIS sensors. One specific product I want to highlight for hydrologists is the VNP 10A15, which is the cloud gap-filled snow product. By automatically filling in areas obscured by clouds using recent clear sky data, it provides data managers with a continuous, uninterrupted view of basin snowpack. When pulling this data, the file prefix tells you which satellite it came from. VNP indicates data from the Suomi NPP satellite, while VJ1 indicates data from NOAA 20. Both satellites provide the exact same suite of high-quality products. You can access all of these version 2 products directly from the National Snow and Ice Data Center, where they are provided in the standard HDF file format for easy integration into your runoff models and forecasting workflows. Now that we have covered how to access iMerge precipitation, SMAP soil moisture, and our snow cover products, the next step is making this global data practically useful by subsetting it to your specific reservoir drainage area. For international applications or large transboundary rivers, we typically use the HydroBasins dataset. This dataset is built on the FastStatter coding system, which creates hierarchically nested subbasins based on topography. The FastStatter code is incredibly useful because it allows you to easily scale your analysis. You can look at a massive continental river system or zoom all the way down to a tiny localized catchment using the exact same framework. If your operations are strictly within the United States, the National Hydrography Dataset is the standard, providing highly detailed, smaller watershed boundaries. By using these shapefiles to mask our satellite imagery, we can extract highly specific metrics for your exact region of interest, whether that is total upstream rainfall, average basin saturation, or the precise percentage of snow cover. This spatial clipping is the crucial final step that transforms global observations into actionable, localized inputs for your seasonal runoff models and water management decisions. I'll now transition to another short demonstration using the web-based NASA Worldview application. This time, I'll walk you through exactly how to easily search for, access, and visualize satellite snow cover data that we just discussed. For those that are following along, click on the link provided at the bottom of the slide to go back to NASA Worldview. And I'm going to use the same reference layers and the same base layer that I used in my previous demonstration with soil moisture. To look for snow cover data, I'm going to go back to the Add Layers button, and I'm going to type in snow cover in the search bar. And we can see we now have 8 different layers that we can choose from for snow cover. 6 of these layers are showing snow cover using the normalized difference snow index. And then we have 2 layers, one from the Terra platform with the MODIS instrument, and the other from the Aqua platform with the MODIS instrument. And these are showing both monthly average percentages. For this demonstration, I'm interested in daily data, so I'm going to take a look at either the level 2 or level 3 data. We have level 2 and level 3 data for both the Terra MODIS as well as the Aqua MODIS instruments. The difference being the level 2 data is detecting snow cover using the normalized difference snow index, but these files are delivered as unprojected 5-minute segments of raw orbital swath at 500 meter resolution, whereas the level 3 data builds on the level 2 data to create a daily composite of both snow cover and albedo. It projects the imagery into a sinusoidal map by picking the best clear sky observation for multiple overlapping satellite passes each day. For that reason, I tend to stick with the level 3 data, but again, that's a personal choice that you can decide. The difference between the Terra Modis and Aqua Modis, because it's both the same instrument, is the Terra platform, the Terra spacecraft, has a morning overpass at local time, whereas the Aqua Modis platform and instrument has an afternoon overpass time. So depending on if you want your observation to be skewed more to the morning or to the afternoon, you can pick either of these data sets. I'm going to go with the Terra Modis daily level 3 data set. And then I'm also going to choose between the Suomi NPP VIIRS and NOAA 20 VIIRS. Again, these are the same instruments on different platforms or spacecraft. They're both less than 1 hour in difference in terms of overpass time. So there's not going to be a huge difference, though obviously clouds can be affected depending on that time of day. I'm going to choose the Suomi NPP VIIRS because it actually has a longer time series. It goes from 2012 till present, whereas the NOAA 20 VIIRS is only from 2018 to present. So that does give you a longer time series if you do go with the Suomi NPP, which is what I'm going to do for this demonstration. And then for the study area, I'm going to choose to go to the January of this year, and I'm going to go to the Western United States because most of the reservoirs out west are actually fed by snowmelt during the spring and summer. And so I'm going to start on January 9th, and we can see, because both the VIIRS and MODIS instruments are optical instruments, if there is cloud cover, it does obscure what the instrument can observe, and there will be some gaps in the data. But we can see as we progress forward in the month, we can see where in the Sierra Nevada and also in the Great Basin in the state of Nevada, we can see that there is some snow cover, and the NDSI is giving a percentage. So if I zoom into the Sierra Nevada, in this case the High Sierra Nevada, and I move my cursor over the snow cover, you can see that in the legend, in the layers pane, it's giving a percentage, 0 to 100% of what the normalized difference snow index is calculated to be a snow cover. So it's giving you some type of confidence or percentage interval that you can choose from. Typically this is scaled, the NDSI is scaled 0 to 1, but in this case, they rescaled it to be 0 to 100 for this case. And then if we go to the Great Basin in the state of Nevada, we can see that there's some of the higher mountain ranges are covered in snow, and as we advance later in the month, we can see that some of that snow melt is indeed melting in between storms. So this is a quick way of accessing and visualizing snow cover data for any geography that you are looking for on the planet, and I encourage you to explore more on your own.
Next, we are going to look at additional watershed parameters, specifically snow water equivalent and runoff derived from NASA's Land Data Assimilation Systems, or LDAS. Runoff is the water that flows over the land surface into streams, rivers, and reservoirs as a result of rain or melting snow. There is also subsurface runoff, which contributes to reservoirs but at a much slower timescale. And snow water equivalent, as we saw earlier, is the amount of liquid water stored in a snowpack. As snow accumulates during the winter seasons and melts during spring and summer, snow water equivalent is released as runoff. In mountainous watersheds, this is very important. Winter snow cover and SWE are vital for determining the total volume of stream flow. Snow melt is a primary water inflow source for many global reservoirs. So both runoff and SWE are crucial for stream flow, which ultimately supplies water to reservoirs. However, there are factors that influence runoff. Not all snow water equivalent is realized as runoff. So amount of runoff depends on rate of snow melt, sublimation, evaporation rates, soil moisture conditions, and ground conditions, such as ground could be frozen or thawed. Depending on that, runoff can vary. Generally, peak winter snow water equivalent is measured to forecast spring and summer runoff, and this is critical for reservoir management for these activities that we have been talking about. Both runoff and snow water equivalent, they cannot be measured directly. They are calculated quantities, and in our case we are going to use NASA's LDAS to get runoff and snow water equivalent data. Here's some information about NASA's Land Data Assimilation System, or LDAS, and you can get a lot more information from the link provided here. Just briefly talking about the model itself, LDAS systems, they integrate satellite and ground-based observational data in water and energy balance land surface models. And as the figure shows here, land surface models solve for the interaction of mass, momentum, and energy between surface and atmosphere for each model element as shown in here. There are several land data assimilation systems for different geographical region and for different purposes. North American land data assimilation system, global land data assimilation systems. There are also specific LDAS is for Western land data assimilation and National Climate Assessment land data assimilation. In this training, we will mostly use GLDAS data, but we will also look at NLDAS data for North American regions. Now, GLDAS data also have multiple land surface models, NOAA, WIC, and CLM, and Mosaic. These models are available globally, and NLDAS data from NOAA, WIC, and Mosaic, they are available for North America. GLDAS and NLDAS have been widely used for multiple water resources applications as listed here. And examples of snow water equivalent from NLDAS, NOAA, and runoff are shown here as time series averaged over Colorado River Basin. The time series goes from 2003 to end of 2025, and it shows how both snow water equivalent has interannual variability, and resulting runoff also shows interannual variability. We will look at all these parameters in session 2 of this training, where we combine all the parameters to look at reservoir management issues. The latest version of GLDAS, version 2.2, that assimilates groundwater information from GRACE and GRACE follow-on satellites, and they provide snow water equivalent and runoff data at quarter degree latitude longitude resolution on hourly and monthly time scales from 2003 to present. NLDAS 2 provides snow water equivalent and runoff at 1/8 of a degree resolution, and they are also available at hourly and monthly time scales starting all the way from 1979 to present. LDAS data can be obtained from NASA Earth Data Search, and they can be accessed, analyzed, and visualized, also downloaded using a web tool called Giovanni. I have just shown some examples here. This is a snow water equivalent in Colorado River Basin. This is winter month of 2000 and 2001, so November to February. And this is the difference of 25-26 winter snow water equivalent compared to the earlier year, like 2000-2001. And you can see that snow water equivalent, the difference is negative here, showing that there's a decrease in snow water equivalent. That means less amount of snow fell this winter in northeast and northern Colorado Basin. These data were downloaded using Giovanni, and so what I'm going to show is have a brief demonstration of Giovanni website, so you can access GLDAS 2.2 without downloading the data and analyze. As I mentioned, in our next session, we will provide you JavaScript code in Google Earth Engine, so you can work with GLDAS data. So I'm going to share my screen and show how to access snow water equivalent and runoff from Giovanni web tool. So I'm going to share my screen, but you can also follow along. You can just click on this link in the presentation in Giovanni, and you will see that window will open. This is Giovanni portal. Let's orient ourselves. There are some analysis options. This time selection, and this is spatial selection. And here you can search for parameters using keyword. On the left hand side, there are many options that you can explore later on. Since we want to look at GLDAS, snow water equivalent, and runoff, I'm just going to search for GLDAS, and we want to use version 2.2, which has GRACE data assimilation, groundwater data assimilation in it. So let's see, we can search snow water, and you will see that this is version 2.2, snow depth water equivalent. We're going to pick that. These are daily data. Kilograms per meter square is the unit. Our spatial resolution is quarter degree, and this is beginning and end date. We can also choose runoff. And search. You will see a lot of other GLDAS versions also. We want to look for 2.2, and here is storm surface runoff. This is surface runoff. You can also look at base flow runoff, which you can add to this for total runoff. We are just going to look at the surface runoff for this case study and for example. Now, there are multiple plot options. So you can plot maps, you can compare maps, you can do time series. There are scatter plots available, histograms and zonal mean, and there are vertical cross section for three-dimensional data. We are going to look at time averaged map and time series, which is averaged over area. We will focus on that, but you can explore all these options for different data sets using Giovanni. Now let's look at specific region. We were looking at Colorado River Basin because snowmelt is very important for runoff and stream flow in Colorado River. That is partially a snow-fed river, especially the upper part of the basin. You can just click on this and then select a shapefile. You can go to Watershed and look for Colorado, or you can type Colorado here, and you will see that North America Colorado Watershed appears here. You can click on that, and this is the basin that gets outlined. Now, for selection of dates, let's look at from 23 January 1st to all the way to March 31st, and then we're going to do that because if you remember in the time series, if you see in NLDAS, the last 3 years there is a sharp decrease in snow water equivalent. So this is 23 was high and now it's low. So that's why we're picking these years. And once you select, you can do plot data, and workflow will launch. Now, to save time, I've already done this analysis, so you can see that the time averaged maps are here in Colorado Basin. This is snow water equivalent, and if you go down, this is runoff. This is also in kilograms per meter square per second. This is total kilograms per meter square. As we saw earlier, in the northern part of the basin, snow water equivalent is much larger. This is the scale here, as you can see, from about 0 to 34.3. And if you go down to runoff, it's of course much smaller because it's per second, but it corresponds higher runoff in this part is associated with snow water equivalent. As you go in the southern part of the basin, this is more because of rain. So this is how you can make maps. You can download data as netcdf file, PNG or GeoTIFF image, and KMZ. And then you can do further analysis either in GIS, or you can use Python or any other programming language to analyze data. Now what I have done is that if you look at the plots, this is the region that has more snow water equivalent. So for time series, I have picked a domain here. So I'm going to go back to data selection, and let's see, I picked data that is this is the time series averaged over 105 west to 112 west and 38 north to 44 north. That corresponds to the northern and northeastern part of Colorado Basin. So now we have, if you go back to data selection, I went back, kept everything the same, but I selected time series area averaged, and here instead of using the river basin, entire basin, I added latitude and longitude, and then if you look at it, this is the box it has selected in the northern part of the basin. And then I just plotted data, and then I got this time series. You can go through these steps now or later on if you want to practice, and you can pick different time windows. You can focus on a particular month if you like, but these are daily data. And what you see here is that 23 of course has had much higher snow water equivalent, and it decreases and it's much lower now. Corresponding runoff also is decreasing, but here there is high variability, and that is because not all snow water equivalent is converted to runoff. It depends on other conditions such as soil moisture, sublimation and evaporation of snow, and terrain. And so weather conditions also matter. There is also rain, perhaps. Snow rate melt depends on temperature also. So multiple factors can control runoff. In general, you do see that decreasing snow water equivalent and decreasing runoff overall, but there is much more variability in runoff. So this is a quick way of looking at GLDAS data. You can also search for NLDAS for a slightly higher resolution. It's 1/8 of a degree, but these are global data, so you can pick other river basins or other areas of your interest. And here also you can download CSV file, NetCDF file, or PNG image for further analysis and examination. So I will stop this demonstration now and go back to the presentation. Thank you. The model products, they include precipitation, rain and snow both, temperature, wind, humidity, snow melt, runoff and surface radiation. So near real time, 5-day forecast and sub-seasonal to seasonal data are available. And more information can be found at these links. Varying resolutions for different models, both temporal and spatial. We will talk about these data products in our next training. We are planning a training where we are going to talk about short-term reservoir management, where weather forecasting is quite important, but we just wanted to introduce these models now. So traditionally, reservoir management uses climatological data to restrict reservoir water levels. But recently, water managers have started using forecast-informed reservoir operations, or FIRO. This approach uses high-resolution weather forecasts to establish dynamic water level thresholds, allowing operators to proactively release or retain water based on impending storm or drought conditions. So for example, short-term predictive capability, 3 to 5 days, as in GEOS 5 FP, allows reservoir managers to track how much water will reach the basin in case of rapid snow melt runoff and prepare accordingly to prevent downstream damage. So our next training will focus on FIRO in using GEOS 5 short-term prediction, and then subsequently we will also focus on long-term prediction and impact on reservoir management. So far, we talked about watershed parameters useful for reservoir management. Now, in the final section for today, we are going to talk about NASA Earth observations and Earth system models for monitoring reservoirs and tributaries.
Now that we've covered how to monitor the water entering our basins through precipitation, soil moisture, and snowpack, we're going to shift our focus directly to the water bodies themselves. Over the following slides, we'll provide examples of how we use NASA Earth observations and Earth system models to monitor reservoirs and their tributaries. We'll explore how these advanced tools and satellite observations come together to help us track water surface elevations, estimate stream flow, and support long-term water management decisions. Let's look at a tool designed specifically for direct water body monitoring, the MODIS Reservoir product, also known as MODE 28. This dataset provides critical measurements for surface area, elevation, storage, and evaporation across 164 major global reservoirs. To put that into perspective, it covers roughly 46% of the planet's man-made reservoir capacity. The methodology works by using near-infrared classifications from the Terra and Aqua satellites to determine the water surface area. From there, it calculates the elevation and total storage volume using established area volume elevation curves. The data is provided in 8-day and monthly tabular formats. Having accurate, regular updates on factors like evaporation and storage is essential for constraining mass balance in our hydrologic models and making confident long-term water supply decisions. To make this data highly accessible, NASA provides an interactive web tool through the LDOPE portal. This allows water managers to quickly plot time series data and download exactly what they need without processing raw imagery. I've included hyperlinks on this slide to both the web tool and the user's guide, so you can easily pull this data into your own reservoir management workflows. Building on the previous slide, we also have the VEERS reservoir product, or VNP28. Like the MODIS version, it provides 8-day and monthly measurements for area, elevation, storage, and evaporation across the exact same 164 major global reservoirs. The key difference is its advanced algorithms. VEERS significantly improves upon MODIS by specifically correcting for terrain shadows, a major challenge when monitoring reservoirs in steep mountainous watersheds. It also features enhanced water classification and improved data quality assessments. The methodology uses near-infrared data from the Suomi NPP and NOAA 20 satellites to accurately map the surface area, and then applies established area volume elevation curves to determine total elevation and storage. Conveniently, VNP28 is integrated into the exact same LDOPE interactive web tool as the MODIS product. This allows water managers to easily plot, compare, and download data from both sensors in one unified interface to support hydrologic modeling. Links to the web tool and the VEERS-specific user guide are provided on the slide for your reference. Beyond monitoring just the reservoirs, we also need to understand the dynamics of the broader watershed. This is where the OPERA project comes in. OPERA stands for Observation Products for End Users from Remote Sensing Analysis. It was specifically funded by the Satellite Needs Working Group to respond directly to well-defined, real-world user needs rather than just research. The core philosophy behind OPERA is to provide free, open, and ready-to-use data with very low latency. This means getting the data into the hands of water managers and emergency responders as quickly as possible. While it is incredibly useful for day-to-day hydrologic monitoring, it is also designed to rapidly support disaster response, recovery efforts, and post-event damage assessments within our river basins. Ultimately, OPERA aims to provide actionable intelligence, data that can save lives, protect critical dam infrastructure, and ensure long-term resilience and water security. I've included a link at the top to access the OPERA datasets directly. Let's review the specific OPERA products available to water managers. The Level 3 Surface Water Extent, or DSWX, dynamically maps changing reservoir boundaries and flood inundation in near real time. The Level 3 Surface Disturbance identifies rapid land cover changes, like burn scars, which is critical for predicting post-fire runoff and debris flows. The Level 3 Displacement and Vertical Land Motion measures precise ground movement to monitor dam structural stability and basin subsidence. The Level 2 radar, both the RTC and CSLC, provide radar products that penetrate clouds and smoke, ensuring continuous observation during severe storms or wildfires. Combined, these offer a comprehensive all-weather toolkit for daily reservoir operations and extreme hazard management. Now let's dive a bit deeper into the Opera Level 3 Surface Water Extent product, or DSWX. This product is unique because it combines multiple types of satellite observations to map surface water. It utilizes optical imagery from the harmonized Landsat Sentinel-2 dataset, as well as synthetic aperture radar, or SAR, imagery from Sentinel-1, and soon from the NISAR mission. By combining optical and radar data, DSWX provides highly reliable, near-global coverage. The radar component is especially critical for water managers as it allows us to map flood extents and reservoir boundaries even through heavy storm clouds or dense forest canopies. The temporal resolution is good, updating every few days, which is necessary for tracking dynamic storm events or seasonal drawdown. Spatially, it provides a 30-meter resolution. This level of detail allows us to monitor not just the main reservoir, but also the smaller tributary inflows and localized flooding across the basin. The product record for the optical data began in April 2023. The SAR data from Sentinel-1 was added in September 2024, and the NISAR integration is expected to launch soon in 2026. To see what this data looks like, let's break down the sample DSWX HLS TIFF file at the top of the slide. The standard naming convention is packed with metadata. It starts with the Military Grid Reference System tile ID, confirming your exact spatial location. Next are the acquisition and production timestamps. This May 2026 example was processed just 2 days after capture, highlighting Opera's low latency for flood response. It indicates the specific satellite used, in this case Sentinel-2C, though it integrates Landsat 8 and 9 and other Sentinels for high revisit frequency. Finally, it confirms the 30-meter resolution and indicates this is Band 1. Band 1 is the basic water occurrence layer, which is our primary focus for everyday reservoir management. Here's a breakdown of a sample DSWX S1 radar file for your watershed derived from Sentinel-1. It uses the same standardized format, starting with the MGRS tile ID, to perfectly align this radar data with your optical data over the same sub-basin. The May 2026 timestamps show extremely low latency, processed just 24 hours after acquisition. This rapid turnaround is essential for active flood monitoring. The file indicates Sentinel-1A radar imagery. Because radar penetrates clouds, it is a critical tool during heavy precipitation events. It maintains a 30-meter spatial resolution, but contains 4 distinct data layers instead of 10. As with optical data, our primary focus for hydrologic modeling is Band 1, the basic water occurrence layer, for mapping surface water extent. Let's compare Band 1 water classifications for the HLS optical and the Sentinel-1 radar products. In both, Class 0 means no water, and Class 1 means 100% open water, our primary class for mapping reservoir extent. The optical HLS detects partial water, which is Class 2, but masks out snow in the code 252 and clouds in 253. The radar, which is the Sentinel-1, ignores clouds completely and adds Class 3 for inundated vegetation, which is crucial for finding floodwaters under dense tree canopies. The Sentinel-1 product also includes terrain masks, which is Class 250 for high elevations and Class 251 for radar shadows in steep valleys. Knowing these values helps you accurately filter data for precise reservoir modeling. With both optical HLS and radar Sentinel-1 products available, how do you choose the right one for your watershed? Well, it comes down to a few key data quality considerations. The most significant factor is cloud cover. If your basin experiences persistent cloud cover, especially during critical spring storms, radar platforms like Sentinel-1 are essential because they see through the clouds. Land cover and soil type also play a role. In arid environments, dry desert sand can mimic the smooth surface of water in radar imagery, causing false positives. Therefore, optical data is much better for dry desert reservoirs. Conversely, if your basin is heavily forested, radar is the best choice because it can detect inundated vegetation beneath the thick tree canopy. When looking at feature size and sensitivity, the optical HLS product is generally more sensitive to open water and has a lower rate of false detections overall. Finally, consider the duration of the hydrologic event. For slow-moving seasonal floods, you can easily use optical data and rely on temporal mosaicing to piece together cloud-free images over several days. For fast, flash flood events under storm clouds, radar is your only reliable option. I'll now provide another short demonstration using the web-based NASA Worldview application once again. This time, I'll walk you through how to search for, access, and visualize dynamic surface water extent data. For those following along, click on the link provided on the slide. This will take us back to NASA Worldview, where we will use the same reference layers and the same base layer that I used in my previous demonstrations. Only this time, when we go to the Add Layers button, in the search bar at the top, we're going to search by Opera. We can see that there are 6 different Opera data products provided through Worldview, but only 2 of them involve the dynamic surface water extent, which is what we're interested in. The first one is generated from the Sentinel-1 SAR mission, and the second is the HLS optical dataset, which is harmonized Landsat Sentinel-2. The temporal coverage for the Sentinel-1 mission is only from December 15th, 2023, so not that long of a record, but we see that the HLS temporal coverage is from January 7th, 2016, so a much more robust data record going back in time. For this demonstration, I'm going to add both of these layers to my layers pane, and I'm also going to add the reservoirs layer that I added in previous demonstrations as well. I'm going to change the date to May 11th of this year, and I'm also in the search bar at the top of the map window, I'm going to type in Lake Mead and zoom into that reservoir in the southwest of the United States. Lake Mead is the largest reservoir in the country, and it's also forms the border between Nevada to the north and Arizona to the south. So if I zoom in and if I turn off or I hide the reservoir layer, and if I also hide the HLS, I can see on this date, I have data for both the HLS DSWX product as well as the Sentinel-1 DSWX product. Now the categories for the HLS are white is the category for not water, navy blue for open water. Then we also have categories for partial surface water, snow and ice, as well as cloud. If I hide this layer and go to the DSWX product generated from Sentinel-1, we have slightly different categories. We have a not water in white, navy blue indicates open water, but then we also have inundated vegetation, a mask for the height above nearest drainage, as well as a mask for the layover shadow effect. So there's no category for cloud in the Sentinel-1 data because the microwaves, the SAR data is able to see through those clouds. And if I zoom in, we can actually see some of that inundated, or what it's classifying as inundated vegetation. Now, this was a quick way to be able to search for and visualize data sets from both the DSWX optical from HLS as well as the Sentinel-1 SAR data, but you could do this and explore this data and visualize data for any other reservoir or study area that you wanted, or study period going back to when these records are kept. So that's a quick demonstration on how to access and visualize DSWX products, and now we will go on with the demonstration.
Thank you, Sean, for the information about reservoir water extent data. Next, we are going to focus on reservoir water level heights. We will look at reservoir water levels from surface water and ocean topography, or SWOT, and other NASA satellites with altimeter data. An altimeter is a radar that emits a pulse of radiation to the Earth's surface from a satellite and receives the backscattered echo, and combined with the precise position of the satellite, the time it takes for a radar pulse to travel back and forth from the surface is used to estimate heights. NASA has a long history of altimeter data, starting in 1992 with TOPEX Poseidon and a series of satellites such as JASON series, Sentinel-6, and finally SWOT. They have altimeters on them measuring heights of water bodies. There are also European Space Agency satellites which contribute to altimeter data time series. Prior to SWOT, the altimeter data, they provide water level height in oceans and large lakes, lakes which are at least several kilometers in size. SWOT, that way, is a unique mission that conducts the first ever global survey of Earth's surface water, captures not only millions of lakes but also rivers along with oceans at an unprecedented high resolution. And this highly detailed elevation data is then used to calculate river slopes worldwide. SWOT is a joint mission developed by NASA and French, Canadian, and United Kingdom space agencies. It was launched on 16th of December 2022, provides global coverage between 78-degree north and south latitudes. Sensors include Ka band radar interferometer, nadir altimeter, and microwave radiometer, and combined observations from these sensors provide very high resolution and accurate height measurements over lakes and rivers. This is an example of how SWOT scans on 20-day orbit cycle, and data provided are global ocean surface topography, land surface water extent, highly accurate water elevation using interferometry, and river slope. SWOT level 2 data products are listed here. The important ones are river vector shapefile, water surface elevation, and lake vector shapefiles. Something important to note here is that future products will include river flow or discharge and lake and reservoir volume change as shown schematically in these two diagrams. So SWOT will measure heights, and based on width of the river and slope can calculate discharge. For reservoirs, change in height along with bathymetry and other information, volume change can also be estimated. SWOT data include water surface elevation and inundation extent in these variables. What is important to note here is the spatial extent and resolution of the data. And the data are available in 128 by 128 kilometers square scene, and within that streams which are wider than 100 meters are resolved, and lakes which are larger than 250 meters square area are resolved. It's much larger, much higher resolution than what was available earlier, which could only sense lakes which were about several kilometers large, and no rivers were sensed then. These are level 2 products for rivers and for lakes. Data can be accessed through NASA Earth Data Search, and there are data visualization and download portals as well, SWOTways and global water measurements, and during this training we will be reviewing both of them. An example is shown here from global water measurements. You can see different lakes, and they are from all past as well as SWOT data, but the time series shown here is for Lake Theodore Roosevelt in the western US. This is from SWOT, starting during the late part of 2023 going to present. You can see height variations in meters ranging from -10 to 15 meters over this period in this lake. So we will have a short demonstration of global water measurement soon. So SWOT reservoir elevation combined with reservoir surface area observed over time can help estimate changes in reservoir water storage volume. Accurate elevation data allows dam operators to know exactly how much space is left in reservoirs. So if the elevation is higher than normal, it can help in flood control, and if it is lower than normal, then water conservation is required. For hydroelectric plants, the elevation of the water relative to the turbines can help assess power generation potential. River slope, together with its width and elevation, river discharge can be estimated for rivers feeding into or draining out of a reservoir. And finally, the river slope and discharge indicate river flow speed, which affects sediments carried to a reservoir at inflow, and so that helps in mitigating sedimentation issue in reservoirs. With that, we'll have a brief demonstration of Global Water Measurement Portal. I'm going to share my screen and go to this portal. You can also follow along if you like. You can click on this link in your presentation slide and you will be taken to the Global Water Measurements portal. We will be using this portal to download some data in subsequent sessions, but I just wanted to give you an overview that what we will be looking at. You can see that there are water measurements, lakes and reservoirs, rivers and wetlands. These two are trial water measurements, ARSET 2 and SWOT. SWOT is the one that we looked at, but it's not complete yet. It will be, but right now I want to share this lake and reservoir portal. You can see that all these dots are lakes, and these are 10-day lake levels. We will be looking at a couple of lakes from this. Just to give you information, there is project background, there are 10-day and monthly data available, and you can learn more about scientific background about producing this data, and there are frequently asked questions which have a lot of information. Then here are the missions which are used for generating lake level heights, and then there are ancillary data that you can look at. Let's look at lake elevation height data. So this is 10-day level, and the colors here, they show variation, or so either above or below standard deviation, mean lake level height. And so blue shows above normal height, and on the orange red they show below normal lake elevation height. Note that these time series are from earlier satellites, and so only large lakes can be observed here. There are monthly lake level data where you see SWOT. All the green dots, they are lakes were sensed from SWOT. In Sentinel 3A, 3B, and VSET are there as well. We looked at one of these time series earlier in the presentation. This is still trial data, and we will look at SWOT data from SWOT-Viz, as I mentioned earlier. But for long time series of lake level data, we are going to use this 10-day product, and you can zoom in, and when you point to any dot, it tells you which lake you are looking at. Let's look at Lake Powell, which is in Colorado Basin. And we looked at snow water equivalent and runoff for this basin. So I'm just going to click here, and then what you see is this is time series all the way from 1992 to present, and this is the lake elevation height. This is with respect to a specific geoid, and these are the variations from -40 to 20 meter. So that's the elevation, and as you can see, the colors represent data from different satellites. The most recent data are from Sentinel-6 and 6A, and then they are shown here for last 3 years. So as you can see in Lake Powell, elevation is decreasing, and it is low right now compared to, say, 3 years ago. Overall, also you can see that there are variations, but then overall there is a decreasing elevation in Lake Powell. So this is a quick way to look at lake level height time series, and we will be working with this data in our next session and two. So here you can download time series data, and we will see more of this in our next session. But in the meantime, you can explore this site. ARSET also had a training which described GWM in detail, and you can find the link in your prerequisite slide for that. There is lake extent data that you can look at. This this is what Sean described earlier. So this site is useful, and we will be looking at some of the data. So I'm going to stop this presentation now and go back to our next parameter. The final parameter we are going to review is river discharge from Group of Earth Observations Global Water Sustainability, or GeoGLOS. So GeoGLOS is a partnership initiative among 100+ national government and organizations to deliver accurate, open and accessible hydrological prediction on a global scale. It is based on European Center for Medium Range Weather Forecast ERA 5 model and integrated forecast system, and that includes multiple satellite data assimilation in the model. GeoGLOS uses a hydrologic model with inputs from models, gauges and satellites to calculate runoff distributed vertically, and uses a river routing model to get river discharge. It provides retrospective and forecast hydrographs for global river segments and provides written periods, monthly and annual averages and maximums, and flow duration curves from the retrospective data. GeoGLOS data can be visualized using Hydroviewer web tool and ArcGIS web map, and the data can be downloaded using Amazon Web Service. We will be using Hydroviewer in our next session to get discharge into several reservoirs, but here is an example of how GeoGLOS can help in monitoring inflow into lakes. So this case study is the water release from Lake Sherburne in Montana. On 29th and 30th of June, there were heavy rains near Many Glacier in Glacier National Park, where you can see Lake Sherburne, and Swift Current Creek brings water into the lake, and there is a dam that controls the lake level. Because of the heavy rain, Lake Sherburne water level increased rapidly, and so operators had to open the dam's gates to their maximum release of approximately 2,000 cubic feet per second, and just to keep the reservoir below its spillway. And typical release in June-July is usually 600 CFS, and so this was much larger because of heavy rain. And this is how GeoGLOS Hydroviewer can help in monitoring inflow into a lake. This is Swift Current segment as it flows into Lake Sherburne. This is the ID for the creek here. And what this shows is Hydroviewer retrospective forecast. So black line is the predicted flow and blue shows uncertainty in the predicted flow. This is discharge in cubic meters per second, and this is time in days from June 28th onwards. What it shows is that this discharge starts increasing after 28th of June, and it peaks on 29th June, and then again it decreases as rain goes down. This is the time when dam operators had to release a lot of water to keep lake level safe. And so Hydroviewer provides 15-day forecast for discharge. So monitoring inflow into any lake using Hydroviewer can be very helpful in assessing how discharge will change and how reservoir will have to be managed in coming days. So this brings us to the end of today's session, and to summarize what we saw, reservoirs are man-made lakes built directly on a river, which are on-stream reservoirs, or they are filled via diversion, which are off-stream reservoirs. They are critical infrastructure for municipal water, flood mitigation, hydroelectric power, and public recreation. Managers balance short-term operational decisions with long-term planning, coordinating across borders, and mitigate water quality threats like harmful algal blooms. Effective forecasting requires monitoring watershed conditions such as precipitation, snow and soil moisture, and reservoir parameters such as water level, bathymetry, and inflow-outflow of water in the reservoirs. We saw that GPM iMerge fills observational gap in ungauged basins, tracking near real-time extreme weather, basin saturation, and long-term droughts. SMAP measures antecedent soil moisture to predict whether precipitation will absorb or become rapid flood runoff while tracking freeze-thaw states. Measuring peak winter snow water equivalent is critical for forecasting spring and summer snowmelt and seasonal reservoir inflows. Moody's and Weir's global water reservoir products provide time series data on surface area, elevation, storage, and evaporation for 164 large reservoirs. SWOT provides high-resolution elevation and area measurements to estimate reservoir storage volume, hydropower potential, and river discharge. And tools like LDAS integrate these satellite observations into hydrologic models, while Opera datasets track dynamic surface water extent using Landsat and Sentinel-2 data. Looking ahead to part 2, on 6th of August, that's day after tomorrow, we'll have session on accessing NASA Earth observations data for reservoir management. So access and monitor watershed parameters, reservoir water levels, and inflow rivers using NASA Earth observations and web tools. Navigate Earth data as the primary repository for finding and accessing NASA satellite datasets. Use Google Earth Engine to map basins via hydrosheds and extract time series data for precipitation, soil moisture, runoff, and snow water equivalent. Visualize regional precipitation and snow cover dynamics using NASA Worldview. Explore specific reservoir datasets utilizing the Moody's and Weir's global water reservoir products. Monitor reservoir water level using the global water measurements tool and SWOTways, and track river stream flow using the GeoGlows Hydro Viewer, and explore global dam information via the Global Dam Watch database. As I mentioned earlier, there will be one homework assignment that will be posted on the last day of the training, that is 11th of August, and the homework can be accessed from training webpage. Answers must be submitted via Google Forms, and homework will be due on 25th of August. Certificate of completion will be awarded to those who attend all live webinars, complete the homework assignment by the deadline, and then the certificate will be emailed to you approximately 2 months after the course is completed. Here's our contact information for myself and Sean McCartney. This is ARSET website and ARSET YouTube links. For questions, comments, or to share how you have applied our training to your work or studies, please email at nasa.arset@gmail.com and join our mailing list to stay up to date on our latest trainings. Visit our contact page to subscribe. Here's a list of resources and references that were mentioned during this session. And with that, we want to conclude today's session. Thank you all for attending, and now we will go to the question and answer session. Thank you. Thank you everyone for attending today's session. We realize it's a little longer and a lot of different data sets were discussed and a lot of information is given to you. Hopefully in our next 2 sessions, we will have more focused discussion using these data sets. So we have a few questions and we will take as many as we can. And I have my colleague Sean McCartney here as well. So we will be going through all the questions. Before we do that, I also want to thank our ARSET team here, especially our coordinator Natasha Johnson-Griffin and editor Jonathan O'Brien. I also want to thank our coordinators, Bob Levins, and learning management expert, Susan Monty. So thank you, ARSET team, for your help. And we'll go to the question and answer session. And Sean, please join in answering the questions. So I'll read question 1. How can satellite observations, hydrological models, forecasts, and reservoir operating rules be integrated into a reliable decision support system without ignoring uncertainty, physical constraints, and local operational conditions?
Yeah, thank you, Amita, and thanks to whoever asked this question. And to answer it, I mean, integrating satellite observations and different models forecasts into a decision support system is pretty difficult. That being said, a reliable decision support system does not force operators to blindly trust satellite data. Instead, it uses Earth observations and model data to constrain hydrological models, and then applies real-world operational rules to the outputs and clearly presents the remaining uncertainty so that managers can make informed risk assessments. Thanks.
Yes, thank you, Sean. The next question is, we have more than 18-month sub-hourly multi-parameter river monitoring datasets such as temperature, conductivity, dissolved oxygen, pH, oxidation, reduction potential, and turbidity, total suspended solids. Which Earth observation products and integrated approach would be recommended for interpreting hydrological events and water quality dynamics? This training focuses more on water quantity. We're not discussing a lot about water quality, but we will be integrating both quantity and quality in our future training. But so there are several sources of hourly data products, such as, say, temperature can be available from MERA2. Precipitation is available from iMerge at half-hour resolution. Water quality data such as turbidity, total suspended solids, and chlorophyll concentration, they are also available at 3 to 5 day resolution from a variety of satellites such as Landsat and Sentinel-2. Maurice and Weirs also contribute to that. And so some of these data sets can be used to combine or compare with in situ data sets. Note that dissolved oxygen, pH, ORP, these are not measured directly from satellites because they don't change water color. And so data available are mostly listed here in this answer. Sean, anything to add?
No, none for me, thanks.
Okay. Question 3, what is the spatial resolution, the size of the smallest visible detail of this data? Is it sufficient for a small local reservoir or only for large basins?
Yeah, I'll jump in. Yeah, I would say whoever asked this, please do refer to the slides 23 to 50. We do provide different specifications for each of these different instruments and spacecraft, so do refer to those. But that being said, if you're using specific MODIS and VIIRS water reservoir products, the data is currently limited to roughly 46% of the global man-made capacity. These are for the 164 major global reservoirs. But if you're interested in smaller, more municipal or just smaller reservoirs, the Opera dynamic surface water product, either the HLS or the Sentinel-1, has a spatial resolution of 30 meters, which will able to contextualize some of those smaller reservoirs that you might be interested in. And then with the most recent mission, the Surface Water and Ocean Topography, or SWAP mission, reservoirs with the size of 250 by 250 meters and larger can also be resolved. So hopefully that helped answer the question. Amita, back to you. Thanks.
Thank you, Sean. So you also want to look at temporal coverage of temporal resolution of these data sets when you consider using it. So either use combined data, or for smaller reservoir, obviously Opera and SWAT data are more useful. Next question also, Sean, you may want to take it. In the NISAR training, we learned that NISAR will provide level 3 soil moisture products. Do you expect these products to complement or eventually replace SMAP soil moisture for reservoir and watershed management?
Yeah, and first off, just kudos to whoever took that NISAR training. Hopefully some other folks on the call took that as well, but excellent training that just took place about less than a month ago. So really great to hear that, or read that this person attended that training. That being said, when using Earth observations, so I think this person was referring to the NISAR, which is an active L-band radar system, and then passive radiometry, which is another L-band, but it's on the SMAP. It's a passive radiometer. That I think they're viewed more as complementary pieces of this puzzle. NISAR provides unprecedented spatial resolution of 200 meters, but because it only launched roughly just over 1 year ago in July of 2025, it doesn't have that long-term baseline for assessing, historical anomalies and establishing long-term baselines. So there's still a lot of value, even though it's a much coarser spatial resolution for that SMAP instrument, for like building that long-term time series. There are also trade-offs in temporal coverage. The SMAP mission provides global soil moisture every 2 to 3 days, while the NISAR has a repeat time of 12 days. So maybe it's case dependent if you need repeated observations, maybe every couple of days, versus if you're able to get by with, maybe once or twice a month for observations, maybe that's sufficient. So that is something to take note of as well. And then just saying the repeat time of SMAP does allow for the rapidly changing antecedent soil moisture within the basin of interest. So these are really more complementary missions, just like all the different missions and instruments we've discussed, how they're really complementing each other to contextualize your own river basin. So Mita, thanks. Back to you. Thanks.
Great. Next question is, does the iMerge precipitation data handle orographic effects to accurately provide data in mountainous regions? This is a common issue with remote sensing data, given the lack of gauging in mountainous regions and calibration bias correction. And that is true. Satellite-based estimates of precipitation in mountainous regions may be less accurate than one in non-mountainous regions. For more information, you can look at this website, the satellite-based precipitation estimates, and what are the challenges, and they are described in here. But you are right. In mountainous regions, it's really challenging to get accurate precipitation. And why is that? That's nicely explained if you go to this website. Thank you. Next question is, what are the best NASA datasets and recommended workflow for developing a near real-time reservoir monitoring system using Google Earth Engine for water quality assessment and reservoir operations? So we will be using Google Earth Engine in next 2 sessions to get analyze some of these data sets and combine them. But note that in GEE, there is data latency and not all the data are available in near real time. So it's best to check NASA Earth data search and worldview that Sean demonstrated to get near real-time data and conduct analysis, maybe in QGIS, or download data that you need and then analyze using some software such as Python or Jupyter Notebook kind of software. So now we are not talking about water quality in this training, but in our future training, we will be talking about integrated reservoir management, where both quantity and quality are included in the training in near future. Sean, anything to add?
None for me, thanks.
Great. Next question is, how can we obtain all these data programmatically via APIs? Do NASA data repos allow SQL queries by external users? You may want to take this, Sean.
Yeah, great. Yeah, we provided a bunch of different options here, which are pretty common for accessing and processing data programmatically. The NASA's Common Metadata Repository API is pretty efficient for searching the entire catalog of all NASA datasets, all different levels of datasets. There's a bunch of different tools like Earth Access within Python libraries for accessing and then using your Earth Data login account to be able to use those notebooks and libraries to be able to access the data. The Earth Engine API, we're going to be covering that in parts 2 and 3 of this training. So you'll be able to see those APIs for accessing through JavaScript, accessing this, and then also OpenDAP and Stack APIs allow you to both access subset and use cloud optimized discovery. And then for the SQL specific question, as NASA moves to Earth Data Cloud, which I think it's about 80% done, maybe more, Amazon Web Service users can use tools like Amazon Athena to query the S3 datasets, as traditional direct SQL isn't that standard for NASA data. And then I believe Amita also provided a link for the Earth data that might be able to help you out as well. So thanks.
Thank you, Sean. Next question is, can this data be used for flood monitoring in the Niger Delta region of Nigeria?
The answer is yes. The data presented here absolutely can. Hopefully, whoever asked that question, if you are able to use it in that area, we'd love to hear from you. Please do reach out to Amita and I on how you're using this data for that specific domain. And then we've also provided a link to a training that Amita led earlier this year, so it's still quite recent, for its more focused training specifically on flood monitoring. The name of that ARSET training is Monitoring and Predicting Floods Using Earth Observations, and I think it got cut off for some reason, but we'll add the rest of the title to that. But anyway, it's a recent training that just took place, and we hope that person, whoever asked that question, will look into that training for more tools specific to flood monitoring. Thanks.
Great, thank you for that information, Sean. The next question, we'll take a couple of questions more, and then we'll answer all the rest of the questions in our Q&A document. So next question is for small reservoirs. Which data sets become the limiting factor because of their special resolution? So basically, Morris and Weirs and then global water measurements, we saw different altimeter data from JSON series and Sentinel-6. They have relatively low spatial resolution. A few hundred meters is the resolution, whereas Landsat Sentinel-2 and SWAT, they have a higher spatial resolution. Again, as we saw in Opera, dynamic water surface portal, data can be resolved at 30 meter by 30 meter resolution, and for SWAT it's 250 by 250 meter resolution. So there's a variety of data available for different resolutions. Next question is, what are NASA data sets that can be used in Google Earth Engine for water quality assessment? And so GEE is limited in NASA water quality data. You will find optical satellite data that can be used to derive water quality parameters. But what we recommend is that you can use Worldview to get data such as water temperature and chlorophyll A concentration and salinity. These are available in almost near real time in Worldview. And there's also a tool, Stream, that we did a training earlier this year on, that provides chlorophyll A concentration, total suspended solids, and water transparency data. Okay. So one question, we'll take one more question. How reliable is GeoGlows in ungauged basins compared to basins with long-term streamflow observations? And it's true that in ungauged basins, it's really hard to assess how accurate it is, because there's no data for bias correction or even for validation. So it kind of varies from ungauged basin to another ungauged basin. It's not the same reliability everywhere. And there is a paper that I just found that describes this issue, that in ungauged basin, how accurate GeoGlows can be or how trustworthy it can be. But since it is ungauged basin, at least GeoGlows gives some data and uncertainty measurements from the ensemble forecast. So you may be able to gauge on your own for the basin of your interest, whether it's accurate enough for decision making. So I think we are at the end of our time today. We have several questions that we will be addressing in question and answer document. Sean, you want to take any more questions, or we can just address them in document?
Yeah, no, thanks so much, Amita. And I will say, for all those that did present a question and we didn't get to it, I know that we ran a little bit over today, but we really appreciate you sticking around. We will be answering all of them. Check back in 1 week on the training page. We'll upload this document and we'll have answered all those questions that came in that we weren't able to address given the time constraint. But I just wanted to thank Amita and the rest of the ARSET team and everybody for joining today. Thank you, Natasha Johnson-Griffin from the ARSET team, for making this run so smoothly. And also Jonathan O'Brien, who's just been tremendous in getting everything edited and posted to the training page. So big thanks to the ARSET team, especially to Amita Mehta for leading this training. And I just wanted to thank everybody for joining today. So Amita, back to you. Thanks.
Thank you, Sean. Thanks to you also that we were able to present so many data sets today, and we'll continue analyzing some of these data sets to get better understanding of how they can be useful for reservoir management. And again, once more, we thank you all for attending today's session. We'll see you on Thursday at the same time. And thanks to our ARSET team as well for their help.